quite unexpected but pleasant surprise. So yeah, let's start, everybody, and let me continue what we did last time, and I'm gonna briefly finish this topic. So last time I was talking about volumes of zonotopes. In particular, if you have a graphical zonotope, G is a graph, then what I explained last time was that the volume of the corresponding graphical zonotope is the number of spanning trees of G, and the number of lattice points of the corresponding zonotope is the number of spanning forests. Yeah. And I gave a proof, and there was some annoying stuff going on. I had to project one dimension down and things like that. So by the way, I think I forgot to mention this. So remember we had a corollary, right? There was a fact, which I mentioned, that if your vector configuration is unimodular, then basically every lattice point of your corresponding zonotope appears as a vertex of any fine zonotopal tiling. Why is that? So I wanted to explain why that's true. So if V is unimodular, which means that each Vi is an integer vector, and the determinant of any several vectors which form a basis is equal to plus or minus 1. So what happens is, let's take a fine zonotopal tiling of the corresponding zonotope. Then suppose here's my zonotope. Here are the lattice points, and then and then I have a tiling, right? So let's assume that maybe there is a tile which has a lattice point inside. Can this happen or not? I claim that this cannot happen. Why can't this happen? I can't hear you. Well, that's actually. So let's assume it's fine, right? So if I'm going to assume that it's fine, yeah, you're right that if there is a hexagon somewhere in there, then it can have a lattice point inside. But let's say every tile is a parallelepiped. Why can't I? Yeah. Okay, right. So in the plane, we have Fick's formula, which tells you a relation between the area of a parallelogram or some polygon and the number of lattice points inside and on the boundary. And actually, so the intuitive idea is that basically because of this determinantal condition here, if you have a lattice point inside, then you can kind of take some smaller. I mean, I guess you can triangulate at least, and you can triangulate your big parallelogram or parallelotope into a bunch of simplices, and each simplex is going to have integer coordinates, and basically there is going to be too many simplices. So the volume, if there is a lattice point inside, then somehow the volume of the corresponding parallelepiped is going to be bigger than plus or minus. Yes, that's the. I don't know if this makes things more confusing or less confusing, but at least the point is that once you know that the volumes are 1, any lattice parallelepiped with volume 1 cannot have lattice points. That's why if you take a fine zonotopal tiling, first of all, because every vector is integer, every vertex is going to be a lattice point, and conversely, every lattice point cannot be strictly inside any parallelepiped. So they're going to be all vertices. Any questions? All right. So yeah, and now let me also discuss the projection issue a little bit. But maybe, yeah, I'm just going to give an example, because I think it should be explained by an example. So let's say I take a graph. My graph is going to have 4 vertices, and maybe it's going to look like this. So the corresponding zonotope is actually, I mean, it lives in 4 dimensions, but it's a 3-dimensional zonotope. So the vector configuration is, I have these 4 vectors, e1 minus e2, e1 minus e4. Right, so I'm just looking at the corresponding edges, e1 minus e3 and e2 minus e4. So that's my vector configuration. And now what I do is I project it down by forgetting the last coordinate. Okay. So after projecting, my vector configuration becomes e1 minus e2, e1, e1 minus e3, and then e2 inside R3. So some edges become weird basis vectors instead of differences of base vectors. And now the claim is that if you take any, so this lives inside R to the, this is n minus 1, where n is the number of vertices. So the claim is that if you take any spanning tree, the determinant is going to be plus or minus 1. If you take any bunch of edges which don't form a spanning tree, the determinant is going to be 0. So for example, maybe I take this spanning tree here, or which one do, yeah, let's say I take a spanning tree, which looks like this. Then I take the corresponding matrix, right? So I take e1 minus e2, and then e1 minus e3, then e2 minus e4, but there's no e4. Just one here. So this is a spanning tree, and so this matrix has determinant plus 1. And then if I take something that's not a spanning tree, something like maybe like a cycle, then I look at the corresponding e1 minus e2, e1 minus e4, and e2 minus e4. And I get determinant is 0. So again, not a spanning tree. This should be convincing. There's exercise. There's prove this in arbitrary dimensions that this works for graphs. Yeah, and right. So now that we are convinced that this works, let me, of course, mention the important corollary, which is the case of the permutahedron. Remember, the permutahedron is a special case of a graphical zonotope. For which graph? For Kn. So remember, the n minus 1 dimensional permutahedron is the graphical zonotope for the complete graph. And in particular, the volume of the permutahedron is what? N factorial. No, that's actually what, I mean, n factorial is the number of vertices, right? So that's what happens to not be the volume. Okay, nice. Yes. N to the n minus 2. That's right. Thank you. And the picture you should have in your head is, here's the permutahedron, and it's divided into 3 tiles like this. Every tile has volume 1. So the volume here is equal to 3. And I guess the next one is, if you take a permutahedron which looks like this, then the claim is that it's subdivided into how many? 16 little cubes. Yeah, so it's an exercise for your 3D imagination too. Yeah, so the next one, 16 and etc. So yeah, this is all pretty cool, and you can also count the lattice points by counting forests, which is also not too hard. Anyways, that's basically the end of the Zonotopes story, although I'm going to return to them every once in a while. Any questions on this stuff? Good. No questions. Then let me erase. Okay, new subject. Hyperplane arrangements. And by the way, there is a book, or rather lecture notes. There is a book is by Stanley, and it's called Lecture Notes on Hyperplane Arrangements. It's free, it's online, PDF, you can enjoy. Yeah, that's actually pretty cool stuff. So I'm gonna follow sort of these lecture notes in some sense, and you feel free to, all the proofs can be found here. But I'm gonna also give some of the proofs, the ones that are easy. So first let me start with the basic terminology. What is a hyperplane arrangement? Which is going to be always denoted by this fancy A. So it's just a bunch of hyperplanes. H1, H2, Hm, bunch of hyperplanes, finitely many. And the hyperplanes are allowed to be linear or affine. Linear or affine hyperplanes in some RD. And right, yeah, so these are d-1 dimensional planes inside R2D. And they can be, right, so affine means it can be shifted, right, so they don't have to all pass through the origin. But if they do pass through some point, then so A is called central. And yeah, pay attention, because I'm going to use these words a lot. So central is, and I'm only going to introduce important words right now. So central means the intersection of all hyperplanes is non-empty. They all pass through some point. I mean, they could have a higher dimensional intersection. And actually, there's also a term for that. So A is essential if actually, yeah, let me draw a non-essential picture. Non-essential picture looks like this. Two parallel hyperplanes in the plane. And why is it not essential? Because the normal vectors don't form a basis. So it's essential if the normal vectors form a basis. Well, then R to the D. And in particular, this notion depends on, like, if you take a bunch of, if you choose some different ambient space, then it may not be essential. And also, so if X, no, it's actually, yeah, that's linear span. Linearly and R to the D. Yeah, yeah, normal vectors. No, there's a word for that too, but we don't need. Yeah. So let's say we let x be the linear span of these normal vectors. Span. Yeah, I'm going to denote normals by hperp. So it's in this case x would be this line right here, and the dimension of x is the rank of A. Rank of A is the dimension of x by definition, and there is something called the essentialization of A. And it's denoted S of A, which what we do is we basically intersect A with X. Take every hyperplane with X. H intersect X. So you get the hyperplane arrangement inside of X. Which X is, of course, a linear space, R to the rank of A. How do I know that they're all what? Right, so that's a good question. So each hyperplane is orthogonal to all. Wait, hold on. So X is the span of normal vectors, which means that yeah, it's well at most one. If you okay, at least one. All right, yeah. So if you intersect the hyperplane with anything, what you're going to get is codimension at least one. You know, or yeah, maybe it contains X, and then it's the whole. I mean, X contains the normal vector to H. So has to be at least. Yeah. Anyways, I'm going to get confused right now, but the claim is that because X contains all the is spanned by all the normal vectors, well, basically the picture looks like this. There's X, there's the orthogonal complement to X, right? And then all the normals of hyperplanes belong to X. So each hyperplane contains the orthogonal complement of X. And there's the section with X is going to be a dimension 1. And okay, so let me continue my string of definitions. What we are mostly going to be interested in are the regions of hyperplane arrangements. A region of A, by definition, you remove all hyperplanes, and you see, and you look at the connected components of what's left. Is a connected component of the complement of A. R to the D minus the union on the hyperplane. And by little r of A, I'm going to denote the number of regions of A. And so that's one kind of important quantity, right? You take an arrangement, you get a number out of it. Combinatorics, that's what we're going to do. And also, I'm going to count not only regions, but the bounded regions. So a region not only bounded by, oh yeah, let me, because of this problem that some hyperplane arrangements are not essential, let me actually say that a region of A is relatively bounded. A region R of A is relatively bounded if the intersection with X is bounded. And let me note by B of A the number of relatively bounded regions of A. All right. Yeah, I think that's enough with the definitions. Let me now play. Let me play with the definitions. Let me draw a few arrangements, and then you're gonna tell me everything about them. I'm only gonna draw two-dimensional things so far. Here are 4 hyperplane arrangements, and first question is which ones of them are central? Yeah, let me say that this is 1, 2, 3, and 4. So which ones are central? 1 and 2. That's nice. 2, but not 3 and not 4. Which ones are essential? 1, 2, and 4. Nice. But not 3. How does the essentialization of 3 look like? Okay, the essentialization of 3 looks like there's 2 points on a line. So these are the 2 hyperplanes. Okay, very nice. What is the rank of each of these? Say 2 for the central one. Okay. And then what? 1. Okay, very nice. Yeah, so here the rank is 1. And what is the number of regions of A? Okay, very nice. And what is, wait, hold on, what? Oh, okay. And what is the number of bounded regions? Yeah, let me actually, maybe I should draw another one. Maybe let me draw it like this. Still not central, still essential. The rank is still 2, but the number of regions is now, okay, 10. Yeah, this is better. And then the number of bounded regions, 0, 0, 1, or 0, or 0. And here, what is? Oh, yeah. 2. Right, okay, so B denotes the number of relatively bounded regions. The actual answer is 1. All right, yeah, very nice. And so the main question is that we're going to study, as I mentioned, is how to compute the number of regions and the number of bounded regions in general. So here you did a very nice job for the most part, but in general, this is pretty hard. In higher dimensions, it's what happened? What happened? I'm trying to fix it. That's interesting. Yeah, I'm not sure what's going on, but it's still recording. And if you, yeah, it's still recording. So if you can just use the remote. Oh, actually, let's see if. Oh, now it works. Yeah, should work now, right? No? Okay, works. Nice. Sorry for the technical difficulties. Okay. Now, of course, yeah, you may wonder, what are the interesting higher dimensional arrangements? Let me give you some examples of interesting arrangements, and then as I'm giving the examples, you may want to try to guess the number of regions. So they're all going to depend on n, For each n, there should be some answer for the number of regions. Examples of hyperplane arrangement. So the first one is pretty easy. So that's called the coordinate arrangement. Which is just given by the hyperplanes x1 equals to 0, x2 equals to 0, etc., xn equals to 0. So these are n different hyperplanes inside Rn. So by the way, what's the number of regions? Number of regions is 2 to the n. What's the number of bounded regions? Relatively bounded regions? 0. All right. Very nice. Now let me yeah, for the next few examples, let me assume that A lives inside Rn, and the indices I and j satisfy, they always satisfy this condition here, I less than j from 1 up to n. So the next one is called the braid arrangement. Braid arrangement. And I'm going to denote it by fancy B sub n is the set of all hyperplanes of the form xi minus xj equal to 0, where I and j are of this form. Okay, what's the number of regions? N factorial. Interesting. Why n factorial? Okay, right. And then, yeah, so basically, in each region, the coordinates are all different, and they're labeled by permutations. That's related to root systems as we studied previously. So what's the number of bounded regions? 0. Interesting. Okay. So, and what's the picture? The picture looks like this. This is n equals to 3. All right, let's do the next one. The next one is called the Xi arrangement. Xi is the last name of a person, and it's given by xi minus xj are equal to 0 or 1. So for each I and j, I have 2 hyperplanes, which may look weird and non-symmetrical. Let me draw a picture. So what do I do? This is the braid arrangement. Then what is the Xi arrangement? I draw the braid arrangement again, and then I shift every. So this is all xi minus j equal to 0, and then I shift every hyperplane one step up. So for each hyperplane, for each of the original hyperplanes, I choose a direction, and then that's the picture that I see. So what's the number of regions of this arrangement? And what's the number of bounded regions? $15. That's close, but not quite. $16. All right. Very nice. What's the number of bounded regions? 4. The rank is 2. Well, in this case, it's 2. Yeah, and so this works for arbitrary n. What is 16 for arbitrary n? 4 to the n. No, that's actually, I mean, that's a stupid question, but actually, n plus 1 to the n minus 1. Right, okay, so this is n equals to 3. This is supposed to be, spoiler alert, n plus 1 to the n minus 1 for some reason. And what is 4 in this case? Well, 4 is actually going to be n minus 1 to the n minus 1. Which, if you think about it, is kind of crazy. Okay, let's continue. So for the next arrangement, right here, I asked you to guess the number of regions. But for the next one, I want you to guess the actual name. So it's again the last name of a person, but for the next one is the question mark arrangement. And it's of the form xi minus xj is equal to -1 or 0 or 1. So I take the shear arrangement and I add one more shifted collection of hyperplanes. Picture looks like this. That's the braid arrangement, and then now I'm gonna I didn't do a very good job with the instructions. No. 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 Yeah, let's compute the number of regions. Maybe somebody can tell me. Oh, what's your guess? Oh, that's actually correct. Yeah. The Catalan arrangement. All right. So why is it Catalan? Yeah, let's compute the number of what? Okay, either 14 or 42. All right, so bigger. Okay, so what's the number? Let's actually compute. I know it's weird for a graduate class to compute the number of regions, but let's actually see if somebody can do this quickly. No. No. 30. That's right. What's the number of bounded regions? No. 12. All right. And these are correct. And these are not Catalan numbers. You're no, don't add them. No, that's not it. Yeah. So yeah, that's the mystery, I guess. At some point, I'm going to explain why Catalan. And the final one is called. That's also the last name of a person. It's called a lineal arrangement. And that's actually I'm not sure I'm going to explain this one, but maybe I give it as a homework problem. Xi minus xj is equal to 1. So I should draw the invisible braid arrangement, and then I'm going to shift every braid one step up. And this looks something like this. So the number of regions is 7. Number of bounded regions is 1. And what are 7 and 1 in general is pretty hard to do, but you can. Yeah, it's possible, but that's a pretty recent result actually. Compute these. All right, let me continue some more examples. The other one is a graphical arrangement. So let's say G is a graph. Which hyperplanes should I choose? Nice. The graphical arrangement is xi equals minus xj equals 0, where ij form an edge of my graph. What is the number of regions? Yeah, first of all, let's do the bounded regions. What's the number of bounded regions? 0. All right. Now, what's the number of regions? That's actually tricky, right? Hmm? Say it again. Orderings on the vertices which satisfy. Interesting. Yeah, I think that you're on the right track. And actually, yeah, so let me actually write down the answer. The number of regions turns out to be the number of acyclic orientations of G. And why is that? I see. Yeah, very nice. Right, so indeed, for the braid arrangement, here all coordinates for any region, all coordinates are pairwise distinct, so you get the permutation. But here, if you look at the region, then some of the coordinates may be the same, but for any edge, the two coordinates are going to be different. So if you direct from bijection between the regions and the cyclic orientations is that you start with the region, and then you orient each edge from I to j if xi less than xj inside R. So perhaps I should draw an example. Here's an example. Let's say my graph looks like this. 1, 2, 3. So I take my hyperplane arrangement is going to have two hyperplanes. One equals to x2, or x2 equals to x3. And indeed, I have four regions. Maybe here, I should choose a side of each hyperplane. So maybe here, x1 is less than x2. Here, x1 is bigger than x2. And then for this hyperplane, maybe x2 is bigger than x3. X2 is smaller than x3. Yeah, actually, these are inconsistent. Yeah, and so basically for each side of each region, I can draw like if I look at this region here, I know that x3 is less than x2, 3 less than 2, and then I know that 1 is bigger than 2. Similarly here, 1 is less than 2. Okay, 2, 1. Okay, 1 is bigger than 2, so yeah, 2, 1. And here it's the other way around. And here it's the remaining, let's see. Here x2 is less than x3, and x1 is still 2. Yeah. Yeah, then let me just use the 1, 2, 3 buttons on the, let's just, okay. Yeah, I think it's gonna work with that. And you can look at the screen to see that I'm inside the picture. So, all right. So you have all these examples. And in some cases, it's easy to compute the regions. In some cases, it's sort of hard. How do you do this in general? What's the machinery? There's beautiful machinery in these statements. So to tell you the machinery, first of all, let's study the intersection poset. Intersection poset of a hyperplane arrangement, which by definition you take L of A is the poset of all non-empty intersections of hyperplanes. Of hyperplanes in A. And then the order relation is reverse inclusion. Ordered by reverse inclusion. You may be wondering why reverse. This is very unnatural. Yeah. Actually, yeah. For hyperplane arrangements, I don't allow any duplicate hyperplanes. So it's an honest set of hyperplanes, of different hyperplanes. Yeah. And what is? But you're on the right track. Yeah. For matroids and stuff like that, you should allow. Yeah. But for now, yeah. For hyperplanes, yeah. Why reverse inclusion? The answer is it's a tradition. Later, we're going to see why it's convenient, but for now, it's a weird convention. And an example is maybe a hyperplane arrangement looks like this. Then the intersection poset is, so let me label the hyperplanes A, B, and C. And let me label the intersection points Y. Then the intersection poset, so it always has a minimal element. There is, if you take 0 hyperplanes, intersect them, you get the whole space. The whole space is always at the bottom. Then there is 3 hyperplanes, A, B, and C. And then there is A and B intersect X, B and C intersect Y. So that's my intersection poset. Is it a lattice? Do you remember what's a lattice? I see. Well, actually, they do have a meet, but not. I see. So X and Y don't have a join. In particular, that's this is not a lattice. Not a lattice. When is the intersection poset of a hyperplane arrangement a lattice? Right. Okay. So A is central. Very nice. If and only if the intersection poset is a lattice. And there's some exercise inside of it, which you should feel free to try at home.